Para começar. Okay.
Next talk is the professor Ivonne Rivas. Invited Diego Souza for introduce the professor. The professor.
Okay. Okay, thank you very much, Mauro. For me, it's a great pleasure to introduce Professor Ivonne Rivas from Universidad del Valle in Cali, Colombia. Professor Ivonne, she defended her PhD in 2011 in Cincinnati under supervision of Professor Binyu Zhang. And she has many publications in very good journals, and she's a recognized young mathematician, work on dispersive control of dispersive equations. And today she's going to talk about the subcontrollability of Boussinesq Equation. So thank you very much for accepting our invitation, and so you can start when you want. Thank you.
Okay, thank you, Diego, and thank you everybody for connecting and stay here for this talk. And thank you for the previous speaker. It was a really nice talk. Not really my subject, but I really enjoyed it. So today I would like to talk to you about the subcontrollability of the Boussinesq equation. This is a joint work made with Eduardo Serpa. He's a professor of, previously when we made this job, he was in the Federico Santa Maria University at Santiago. And now I think he moved to Universidad Católica, also in Santiago de Chile. And at the end, I will also would like to talk about a new problem that I have been working, and the paper is submitted but not yet answered. So okay, first of all, so I will introduce the equation of Boussinesq. So here's Boussinesq. So this equation that I described it here is a PDE equation with the function. We have it in space and time. And more than that, this equation was generated for him as an answer of a challenge of Russell. I don't know if you already have this part of the story, but I would like to say it. He saw this way of translation, and he was asking to the math community to try to make a model or mathematical explanation about this wave that was translating without changing the shape and the size, just moving like a photograph that we paste. This way of translation, now they are called solitons. So Boussinesq actually was the first person that did the answer to this model. So he proposed this equation. Okay, this is an undimensionalized equation of that one that he proposed. The original, it has some constant here, but basically the terms are the same. And even this equation was first on the Cortebret-Debrec, that is very well known as a KdV equation. Boussinesq in his paper, if you go to see the note in the bottom, the footnote, he proposed the KdV equation making some approximation in plus or minus infinity to 0. So it will negate some quadratic terms, so you will get the KdV equation. However, the Boussinesq equation that he was concentrated in proposing was the second order expansion of his model. So this is kind of one big difference between the KdV and the Boussinesq. So this has been studied, but not as much as the KdV. Also, the problems that we can find in one and the other one are quite different. So in this talk, basically, I will concentrate on this equation. This is the original. This has the nonlinear term u squared with two derivatives in space. However, the result and most of the paper has on a bit generalization of this quadratic term. Since it's a two-space derivative equation, so we will need to have two initial data, one in, I don't know, in u and one in his derivative, if you want to change in the position and in the velocity. So we would like to know in which spaces this problem is controllable actually, but to answer the question about controllability and to explain you what is that, so first I will need to address the problem of well-postness, because we need to know first what kind of solutions they are. Okay, the well-postness basically is based in to know if the equation has a solution, it has a unique solution, first existed, second uniqueness, and third continuous dependence of the data. So if we said this is the definition, and if we said that, so we will need to think in another problem, like which spaces actually I will put the initial data to get the solution as I want. And also to know that we have to set which domain we want to work. So first of all, I would like to make some state of art. Okay, I have to go back here since I say this data here is in, okay, we have the same space, like let's say that we will work with solar space. So in a space, in a space variable, I mean, and here this will be the derivative, yeah, of the previous data. So that I want to say, if I fix the space where I'm working for this data, so it will give me some kind of irregularity that I already have this one. One thing that we have to see here is that since we have two derivatives of time, and if we see the higher terms in a space that is four derivative, so we had a relationship between time and space 2 to 4. So that is why, sorry. That is why we will have that our initial data will be in some HS, and the second, or the time derivative of the second data, I mean U1, sorry, will be in H minus 2. So I need to translate the regularity from from time to space, actually, to be able to have this difference of power of index. Okay. So if we have that clear, so okay, sorry, it shouldn't be the torus here yet, but this is the space that actually we got our results. But since I'm making a state of art, I would like to go over some results that are known about the Boussinesq in general. So the first one is that in R, in the whole line, so we know that, okay, in this case, you should put here the whole line. So you had that Bonan and Sack in 1980. They proved global well-postness for S bigger than 1. So they use energy estimates for having this global well-postness. And this result was improved by Felipe Linares in 93. Proven as well a global well-postness for S bigger than 0. So for one big difference between these two results, okay, since you get to S equal to 0, I mean L2, so you have to use some different techniques. So he was using more in this case a Strickland estimate that actually he formulated in his work. Some years after, okay, many years after, in 2009, Luis Farag, he proved global well-postness, but he dropped the index to negative side, I mean to -1,4, bigger than -1,4. So for that, he have to use some much different techniques than the two previous one. He have to go to deal with bilinear estimates to be able to deal with the nonlinearity, and he proved actually that for S bigger than -1/4, so the Boussinesq equation is well-posed, locally well-posed. No, this result is not global. And this is the last result that we have, is the Kishimoto and Sugawa in 2010, when they improved the result of Farag to -1/2. I have to say that these two paper, or these two last results, they are quite different, and I will make a little bit explanation of those because we use it for our results. And one important thing, sorry, I have to go back a bit here. One second. When I go back. Okay. Here. So one of the things that the authors of the previous the result that I'm talking to you use is, if you combine just the two first terms here, so you can see that the Boussinesq equation can be decomposed or can be factorized if you want it into heat equation. So here, so you can start it that way, but you have to remember that when you have one of the signs, you can have some problem of impulsiveness. Also, you can combine these two terms, this one and these two, the two derivatives in time and the four derivatives in space. And if you make another decomposition, so you will find out that the Boussinesq can be written as a two Schrödinger equation going in different directions. Also, if you just consider this way, okay, you can have some result of the wave equation. So there are different ways that you can approach to this problem. For example, Farag, he used the Kiribi approach, but Kishimoto and Sugawa, they use the okay, no, they also use the Schrödinger equation, but totally differently than Farag. Now that really, I will explain you this a bit later. Some other results about the Boussinesq equation is in the half line. This is the last study, was made by Xu. He's just proved that it's locally well posed for S equal to 0. I have to say that, okay, since this is air plus, so we need to have a boundary condition in this case, so that made the problem a little bit harder, or quite harder. And maybe that's why this is the only result known. And for the torus, so we had also, it has been very well studied. Some of the results just go from the studies in the whole line. So we had this of Fan and Grijarki. They prefer between 0 and 1, the local well-posedness. So in here, we can consider this as a boundary problem with periodic condition if you want. It can be addressed in that way. Farag and Sialom, they prefer S bigger than -1/4. This result is some of the ideas of the result in R. This new one for S bigger than -3/8. So it's made that by Sunglin and Stefanov in 2013. In this case, these results are just made for local well-posedness. And Kishimoto also proved some results for the torus for S bigger than -1/2. They use basically the same ideas of the when the domain is the full line. So in this case, so as I say, I will go back a bit about this. And at the same time, Xu also addressed the problem for the boundary, okay, for an interval. So this is much complicated. And he proved global well-posedness, but just in this interval, and when the boundary conditions are homogeneous. So still a lot of things to be addressed in this problem. Okay, this is the thing that we know about global well-posedness for the Boussinesq. So I will show you the problem that actually we study. Is the Boussinesq equation. In here we had any combination of quadratic combination of function of u. In this case, I will just write it this way as a nonlinearity, and we need to consider also some forcing term. In this case, we have the problem set in the torus. So that is similar to give this kind of conditions. And the forcing term, we will take it in this particular form. Why we are considered this way? Because our purpose is to study the controllability. So later we will consider that this is just a localized function, and in reality, this is going to be the control that we want to take. So, okay. So since it's the localized function, so we want it to be supported, but not in the full interval. So the controllability has more sense. Okay, since we are considering the torus, so we need to set some spaces. Specifically, we will have this norm. We will consider the solid spaces as you know it, but with the series, with the Fourier series in this case, and we need to add this condition that the mean is 0. So the problem actually had some sense. Anyway, if you try to make this computation in the equation, so you will need that this is something that is required to the problem. Here I haven't told you about the S. We have it for the linear part free, but for the nonlinearity, we will have some restriction about the S index of the solid spaces. Okay, so I will say some words about the work first of Farag. Because he proved for S bigger than -1/2. So, and this is the ideas that we take from his work. So basically, we go to study the operator of the Boussinesq equations. It has two derivatives. We have to write it in a matrix form. We consider to have sense just the periodic solid space with 4 derivatives. I have to say here that we are considering this parameter, but after some time, due to the difficulties, so we will consider it 1. But this part, it doesn't matter what we consider for lambda. And after, okay, so this we have this operator, and for this operator, we will study the spectrum. So we have that the eigenvalue are given by this lambda sub k, and it has over the natural positive and negative, and something that made easy or more complicated, I don't know, you will say, that we will have this expression that we will have plus or minus in front. So if we go to the Fourier space, so okay, we will have to take k over n, and we will need to consider this type of matrix. So we can use some to find a similar matrix just to make it more simple to study. So it's studied this one here, and we can diagonalize basically this matrix. So when we do all that, we can find that the solution is given by this expression. This is nothing, can look scary, but if you see, if you diagonalize this matrix, okay, you will have your eigenvalues here that are no more than this, and you will have two matrices next to it, and of course this will have to run over all n, no, or all k in this case, and so you basically when you diagonalize, so you can associate one part here and another part here. That okay, you can forget about the nonlinear problem for a while. So you can have these two as the semi-group if you want to think about it, and multiply it by the initial data. In this case, this is the U0 and this is the derivative UTX0. So if you apply Duhamel, so you can have the rest of your part, okay, the part that you have the forcing term or the control term after as you wish, and you have the nonlinear part. And since the decomposition that we are making to write it in a matrix way, so that will give us that actually for the forcing part, for this part, we just will need the second one W1. So to be written in a better way, so here is the expression. Something important to say is this is a really, really good term. It's kind of perfect that we need. Why? Because U1 is losing two derivatives with respect to U0. And here when you see this expression in here, okay, this is a square root of n4, so I mean there is n2. So it's exactly that you need to balance it or to equilibrate the regularity with this function here. So it's just exactly what you need. So this is a really nice expression, and this is no more than given for the expression when you diagonalize and make your computation. So this expression came out quite nicely. So, okay, so with this in mind, and okay, since the idea is to drop below 0, so we will need to work not just with solid spaces, but we have to go to work-gate spaces. So these are the work-gate spaces suggested for the Boussinesq equation, and the problem is local. So we will need to make some restriction to have it in the local in the interval of time. Okay, so this is kind of the big details of the Farad work, and the most important or the more relevant for this work was this estimate here that is a bilineal estimate. Okay, we have the normal estimate for the first part, for the linear part, and also we had this bilineal estimate that is quite important, okay, for the well-posedness of the full Boussinesq equation, but also will have some relevance in the controllability. So they prove it just for s bigger than -1/4. I can go back 1 second to explain something. If you try to see this expression here, I say that it was related with the Schrödinger equation because this term is just a quadratic term, n over quadratic term. If you consider n positive, so here you will have the Schrödinger equation I zeta squared if you want to think it fast. And this one is going with minus, it's going to the other direction. So that is why it's highly related to the Schrödinger equation, and the result, okay, is expected to be equivalent, not equivalent, like has some similar. Okay. So about the work of Kishimoto, so we had he studied between -1/2 and -1/4. It's important to say that in his work he says, and actually you can check it out, that this result just apply here because for bigger you have to go to the work of Farad. So this idea that he addressed here is just for this interval. What he does, basically, he writes the Boussinesq equation in this way, which is not so simple to see, but you see here that, okay, you have the Schrödinger plus nonlinear terms, kind of a quadratic nonlinear term, if we forget omega, but omega has this part here. Okay, this is kind of order 1, so it will be a quadratic term. And if you make this chain of variables, so you can get the Boussinesq equation. So what he does is making some transformation of the equation, and you come out with this one. And since you are making the transformation, okay, the initial data is given by this. It's important that actually this transformation will give us the solution of the Boussinesq when you consider U as the real part of V, and the initial data is given by this part, like the real part of V0, and you have to make use this operator actually to get the second component of this solution to get the U1 in the case of the Boussinesq. So this is the way that he addressed it. So he also get a bilinear estimate. The bilinear estimate that he gets and insists is just for this interval and is given by this way. the most important part for us, that actually we can drop and our results can go until -1/4. Okay, so now I would like to present the problem for the controllability. So we had again the Boussinesq equation, and the forcing, now it's not going to be just a forcing, because we would like to address the problem. What is the control problem? We have two initial data and we have two final data. Okay, I say two because we need two data in this case. So we had initial data, we have final data, and we would like to get from one position to the other one, but using the forcing term F, that now we will call it control term, and it will be showed here in the H part. The control that we are considering, it has some space and time part. Okay. So there are different types of controllability. The one that I'm talking about is the set controllability. So we are setting here well initial data in the spaces that I already explained, HS and H-2, and the final data in the same spaces. And I would like to find H, and okay, sorry, and H we would like to together in L2 HS. So since the linear part, we have to address the linear problem. For the linear problem, we don't have any restriction for the S. So we would like to find an uncontrolled H such that solve this equation, satisfy these conditions, and start in the U0 and UT, and in time U0 and U1, and in time T, go to UT and U1 T sub T. So this is kind of the problem that we have. We know already for the well postness that if we have a fix and the data fix, so we have a solution, we have a unique solution. Now the problem is different. We have this set of data, and we would like to find F or H in effect as such that the U is a solution of the problem. Okay. So the way to address, okay, sorry, the state of art that we have for this problem, it was started by Sang in 98 and Crepeau in 03. The control in both cases is in L2HS. The first work was in the torus and was starting also was made by starting the momentum method that is studying the spectrum of the problem. And Crepeau also studied the problem, but this one is in the interval. He used to set a boundary condition. This is the first one, putting the control in the derivative space in the right side. And the second set that she used was with two derivatives in a space, also in the right side in L. In both cases, she got a set controllability, also using the momentum technique. That is also the technique that I will show you. Okay, so in the word that we made, we want to study the operator A, as I already defined it, but here I'm giving a little more detail because I would like to write the solution specifically in terms of the eigenvalue function. So these are the spectrum, and the eigenvalue that the eigenfunction, that we have is if lambda is equal to 0 is this one, and it is okay. So if it's drawn in the integer numbers, we just have that is this case. Actually, this is a risk basis. It's given in this way, which is quite nice because it's the exponential. It's kind of it's related to the basis that we would like to have. So this is the spectrum for the Boussinesq. Okay. So we go to write our solution of the problem. Since we have the spectrum, so it make a basis, so we can write it. And so the solution of the equation will be given by, okay, this expansion. This is the expansion, and for this part, we just use the Duhamel term. But this term, we also write it in the way of the expansion of the bases that we have here. The bases are eigenvalue. Then we need the eigenvalue to be able to write, okay, the semigroup. But now, if you want to think, is diagonalize. So we have this here. So what we want, I will go back to the previous, sorry. Not previous. So I need the solution in the, sorry, here. So what we want, we have this solution that I show you here, basically. And I want to write each of this term now, since this is kind of the semigroup. So we can write it in terms of the bases. So we rewrite every of these terms in the bases, but not in any bases, in the bases given by the eigenfunction of the operator. Yeah. And our problem actually is to find H, or G if you want, like the control that is given here. You see, we don't know. This is the guy that we want to get. So the rest, the initial data we know it, the nonlinear term is depending on the solution. This, okay, we don't specifically know it, but we know some information, but about H, we don't know anything. So this is what we want to get. So in this new way of writing here, so I will translate a bit. This part is the initial data. Yeah, this is given. This part here, the initial data. No, this part here is given by the initial data. So the beta 0, the beta n plus, and the beta n minus, we already know that. So in this part, we know the expression. For this part here, we don't know alpha, because alpha is related to the age. So this part of this kind of projection that we have here, that is the part that we are interested in finding. So we need to find alpha 0 and all this. So in this one is actually the problem that we would like to get. But as I told you, we know things. We know that here, we know the data. This is the data at 0 or at time 0, this is the data at time t, so we can go to write the solution in these two cases because we have everything. So if we do that, so we can write, we just replace 0 and write this and replace t and rewrite this. So we would like to find the alpha in here, so we can do it. So if you do that and you take into account that these bases that I show you, these eigenfunctions, there are the bases that I showed you before, they are orthogonal. So we can write this in this way of the end. So it's good because here we have the alpha 0, alpha n minus, and alpha n plus, and okay, and everything of this side we know, and the beta we know. The gamma here are from the final data, and the beta are from the initial data. But alpha also is related here. Okay, or here, this is more general, with the eigenfunction, but h, and this computation will give us a function on time. Yeah, so this is not so simple to take out from this integral to actually to say, yes, I know alpha is given for this expression. So we will need to use another strategy. That is that since we have arrays basis, so we can get, in this case particular, because this base is in the closest span of the Pn, so we can get B orthogonal bases. Remember that H is not just in time, that this basis is given in time, and the age, that is the control, is written in time and space. So we need to have this also. So to be able to simplify the expression through the integral, so we will need to get this new base, or this be orthogonal base Q, such that that is orthogonal as we want. So the thing that we do is just go back and write h, just h, in terms of this new basis, so of the b orthogonal basis. And okay, we can write it this for some h that we don't know them. And okay, this is the rest of the part written also for h minus and h plus. Why is this important? Because this really will help us to to solve this system. So doing that, so it's very simple. So we go back and plug here our h. Okay, this alpha 0 in reality is given by this in inner product. So we can rewrite this. Okay, I didn't want to annoy you with the big computation because actually they don't say anything. I prefer to explain you. So you can write this in the inner product, taking into account that h now is written this way, apply the integration, and since you know that many of those are going to become 0, because this is just the delta chronic, so we really will be known, will be found, we really can find h minus, okay, hg minus and hg plus without problem. It becomes really a easy system to solve. So in that case, we can give our representative of h. And okay, the problem is not just done that in there, because in this moment we just say, yes, we had h, depending on the initial and the final data is given by this expression, but we don't know the regularity of the h. So also it's necessary to make some computation to estimate in which specifically space will be written this h. With the condition that we find in this part of the computation, is easy to prove that it's in the appropriate space. In this case, the space with the control will be is h minus 2. So with that, everything that I say taken into account, so we can formulate, or we can write the operator that it takes the initial and the final data, and it gives me back the control that I need. So in this case, we call it that way, and h is specifically the control that we need. And this operator is going to be continuous. This is quite nice, and we will need it. So with that into account, okay, at this point, we already have the exact controllability, we have the kind, we have the age, we have the space, everything works. We can say we have the exact controllability for the linear case. Now for the nonlinear case, so we will need to consider, okay, again, the expression, but now we really need to take this part into account. What we do in this case, we use it as a perturbation. That's why this result is local. So for making us a perturbation, okay, we use a very traditional technique that we state W of t, that is just the nonlinear part of the problem, and we write h using this operator that you give me initial data and final data and gives me the control. But in this case, we will use a very particular final data that it would be U1, that one that we have actually. Okay, these two are the initial data and these two are the final data in my operator. But here, particularly as initial data, I will take the nonlinear part included here. So, sorry, this is final data. Final data, we will have the nonlinear part included here. We kind of try to manage to work it as a linear. If you put this to the other part, so you just plug T, capital T, and plug this to the other part, to the other side here. So you can say that all this is your final data. So your theorem can apply exactly as we used it before. And this is good because then we have that since this is continuous, we had estimates. So if we write now a new operator written this way to use fixed point theorem, So we basically we are done because we had estimate for this part. Depending on the S if you take S bigger than -1/2, okay, you can use a Farad estimate. If you take it until -1/4, okay, you use Kishimoto bilinear estimate. So in any case, you can use it. And you have that this part is estimated. This part is estimated by the previous result. And even this part here is estimated by the Farad estimate or Kishimoto estimate, as well as this one. And since both authors have included quadratic terms here, so the result can be written as a quadratic term. And okay, and that is everything for the Boussinesq equation. I had 4 seconds. This was the other problem that I wanted to mention. Maybe I don't have too much time. So this is a kind of generalization. This is really a generalization of the, if you want to think, this is the Boussinesq operator with lambda here, but we are taking the nonlinear term different. This is the KS estimate. Sorry. Kuramoto-Shibashevsky equation. So fixed in some intervals. So many of the estimates can be think as the same way, but the Kuramoto-Shibashevsky has a big problem for this lambda term here, that it has to be considered in a specific interval. For if you, okay, the Kuramoto-Shibashevsky is one derivative in time, but you can think if you study just the operator and then give values, okay, you can find some information, and this is kind of problematic equation because the spectrum is not as nice as the Boussinesq. However, not even is Kappa joint in the natural norm, so it's possible to set interproduct, so and also some restrictions over lambda in this case, to get a norm enough good to get it as an adjoint problem. But this is just talking about well-posedness. For well-posedness, also there are some issues to be addressed because this nonlinear term with this operator, it has never been treated as far as I know. And so this is a really nice problem and a new problem to be studied, not only for the controllability point of view, but also for the well-posedness point of view. Okay, here I put setting it in the interval, but there is no result even in other domains. So I was able to prove the controllability when we use H3 in this case, everybody else is 0, but in the linear case. Okay, or for the nonlinear case, for S bigger than 1/2, that is actually when we can divide this part. Okay, this is everything that I wanted to say today. Thank you so much, and sorry for the little delay.
Okay, Ivonne, thank you very much for this wonderful talk. So now we're gonna open the turn for questions and comments. So if anyone has a question or comment, please open your microphone or raise your hand or type your question in the chat. So I have a couple of questions, Ivonne.
Yes.
The first one is that, okay, for the linear controllability, the controllability for the linear equation, you use the moment method, right?
Yes.
And do you have an idea about the cost of controllability in for the linear equation?
No, I don't have an idea because here we don't really estimate, but the observability, the observability inequality. So we never see the constant. So, but however, I just thinking fast about it. Since we have the candidate and we have some expression already written for the solution, maybe it's possible to do a study. We plug that there and to see what is the sharp constant that it can be written in this inequality.
Yeah, I know that recently people did some study of cost of controllability for the parabolic equation by using the moment method. They in some sense they use they estimate the bi-orthogonal family. They get some bound of the orthogonal family in terms of time, and then they get the cost of controllability. And I was wondering if you have some. You see here you have the P of n, which is the exponential family, and then you control. In fact, you get in terms of this bi-orthogonal family, no?
Yeah.
Yes. Yeah. So, okay. So this is the first question. The second question that I was thinking was about the bounded domain that you formulate at the end. Yes, this one. So, and also you have some. I mean, for the linear, I didn't see if the time it should be large enough, or I didn't see that.
No, the time doesn't have any since it's the linear, so we are not using fixed point or anything, so we don't have time. That is no the real issue in here. The issue is how to control the spectrum by itself. It has problems.
No, I mean, in the case that you treat, which was in the torus, right?
Yes.
Okay. In the linear case, I mean, you do not have any constraint about the size of the capital T, no?
No.
You okay? It is because the equation is really similar to the wave equation, but and for the wave equation you have that the time it should be large enough, but in this case, no. Okay.
When I did the computation, actually, since I was in this condition here, I remember that the issue of the time, because I also thought about it, was kind of replaced by this condition. It's kind of it will satisfy when I put in the condition over lambda. I forgot to say that this is a very sensitive equation. You cannot put any lambda here. For example, if we just think in large one, yes, and one in here. If you put one negative, so we get exactly the Boussinesq equation, and this is well posed. But if you put lambda equals to -1, we get the bad Boussinesq. I didn't mention the difference between these two, but the bad Boussinesq is not well posed. So we already had some restriction in here. And the condition of the time that you are telling me, I remember it was addressed, like the condition was addressed just taking this condition over the lambda.
Okay. So you take this condition in order to make the result valid for all time t, right?
Yeah,
something.
But basically, the thing is, if you consider the equation without restriction, you will have some eigenvalue, some positive eigenvalue. Even if you know that they are bonded, because okay, this spectrum has been very well studied for the Kuramoto-Shibashevsky. But since you have this positive side, so this can make some problems to you. So when you put this condition in the NR, so actually you are moving it. So your spectrum becomes 0 or negative. So that saves the day.
But if you do not have this condition, you have only a finite number of eigenvalues which are positive, no?
Yes.
And these, yeah, perhaps you can do something. Okay, and my last question, and in fact is something that it was not clear for me at the end, is when you get your nonlinear controllability result, at some point we need that initial condition, the data should be closed, no? Or not? Or you get that for, is a global controllability result?
No.
No? And at which point you...
We don't have global because we don't have global estimate for well-postness. So we are using the estimates here in this for this part of Farad or for Kishimoto, and they are local. So if you, I think I showed them. Sorry, one second, I go back. For example, this you know.
Okay.
The estimate is with tiny here. So if you want to make contraction, actually you want it to
be... Yes. Okay. Perfect. Thank you very much. Okay, so is there any other question or comment? If not, let us thanks again, Ivonne, for this wonderful talk. Thank you, Ivonne.
Obrigado, Ivonne.
I give the word
Obrigado,
to
Ivonne.
Mr. Mauro.
Parabéns aí pela fala, pela palestra, tá? Seja bem-vindo.